Good morning. Today we will discuss the applications of what we did last times. And let me recall you the general instruction which we already did. We considered a real separate Hilbert space H. In this space, we considered Gaussian white noise. What is it? If dimension of H is less than infinity, then psi is simply a standard Gaussian vector with zero mean and identity correlation. But in case when dimension H is infinity, then psi is not a usual random element in the space H, but it is defined as follows. We considered a sequence of IID standard normal variables, then orthonormal basis in H, and finally define this psi as a formal sum psi is equal to sum from k equal 1 to infinity, psi k. We discussed that this is just formal sum because the series doesn't converge in H in any sense, but one can define properly for any H which belongs to our space the inner product with psi, H psi, which is as usual the sum of coordinates product psi k, h k. And this series converge in L2, in any LP, and every shoe. And the result is the Gaussian value with such parameters. So we haven't psi as a random element, but still we have a family of its product with different elements of our Hilbert space. Then we discussed representation of random variables which are square integrate and measured with respect to this sigma field, smallest sigma field generated by this family. Or it's better to say generated by this Gaussian white noise psi. We discovered that if alpha belongs to L2 sigma psi, then it can be uniquely represented as a series which converges in square mean of the following sum of the following summas. This is an psi where an itself is an element of the symmetric part of tensor product H on itself, or in other words, an is a Hilbert-Schmidt n-linear symmetric form defined on our initial Hilbert space H. And this random variable an psi is defined as sum from E1, En equal 1 to infinity, H, E1, En, here is psi E1, psi En. In this formula, A and E1, En are coefficients of the form an in the orthonormal basis, for example, introduce it right now, ek, and this star means that we take not usual but weak product of this Gaussian random variables. In this case, it means that in this product we collect random variables of the same kind. For example, if we have here psi1, psi1, psi1 3 times, then we substitute this degree by the Hermite polynomials of the same degree. Then it occurs that such random variables exist, that the rest converge, and moreover, they play a role of the infinite dimensional analog of Hermite polynomial. So one can consider this chaotic expansion of the random variable alpha as the infinitely dimensional analog of the expansion of the random variables with respect to Hermite polynomials. After this, we introduced stochastic derivative of the random variable and a joint operator to stochastic derivative, which we called extended stochastic integral or stochastic integral. Let me recall you what it means. We discussed that d alpha, if it exists, stochastic derivative, is an element of A2 omega pH. So it is not random variable, but a random element in H, which has second moment of the norm, such that for any H which belongs to our space, we have the following equality: d alpha H is equal to sum from n equal 0 to infinity, and H psi. So here we have n minus 1. And you see what is happening here. After we substitute in one coordinate into an our vector H, testing vector, then we get from the n linear form n minus 1 linear, still symmetric Hilbert-Schmidt form. So we still can organize this n minus 1 degree infinite dimensional Hermite polynomial and organize the sum. Of course, it can converge, it can happens that it does not converge, but we suppose that this thing exists, and in this case, it must be of the following kind. We denote it as usual by W1, the set of all stochastically differentiable random variables. And finally, we introduce it. Finally, we introduce it E like a joint operator of D, and E is acting from A2 omega P H to A2 sigma psi. Of course, it is not defined for all random elements which has a second moment, but it has a dense domain of definition. And we discussed that D itself and E as a joint operator, of course, are closed operators here. So we have good properties for these operators. Even one can find a representation of E of X. What is this? How do we find it? We suppose that X H for any H from our space is expanded B and H psi psi psi. Here we have n coordinates, and it is natural because the left-hand side is square integrate random variable which linearly depend on H. So it must be represented as a sum of a Hilbert-Schmidt form from our side, but this Hilbert-Schmidt form depend on initially additional coordinate H. And despite they are symmetric with respect to last one n coordinates, they're not necessarily symmetric with respect to all coordinates. And it occurs that this square root integral from x is the sum of the following type. Lambda bn, here is psi, 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 where here we have n plus 1 coordinates, and this is symmetrization. This is symmetrization of the our form Bn with respect to all coordinates. Okay, so it was a formal construction with good properties. Moreover, in case when we have, for example, one-dimensional Gaussian noise, just in case H equal to R, we have seen that for a random variable to be stochastically differentiable, it needs to be represented as a good function, at least continuous, and moreover Sobolev function from the Gaussian random variable psi. So we expect that using such kind of operators like D, I, and connected with them, we will build another one. We will be able to discuss properties of the functionals from white noise and make some conclusions about it. But before to do this, I think that it is time to have a good example of infinite dimensional Gaussian white noise and example of this abstract construction. So let us devote this lecture to the maybe one of the main examples of the previous construction. Namely, we will consider let us say white noise related to Wiener process. White noise related to Wiener process. So let us why I'm recalling Wiener process to you in this context. Because all of you have an experience about the different families of Gaussian functions. Namely, you know that when we have standard Wiener process, then one can construct Ito stochastic integral for random functions, a random function say x t, which is adapted to ft. This is a sigma field of the past of the Wiener process up to the moment t. So one can consider the stochastic Ito stochastic integral and this integral is L2 limit and n tends to infinity for good functions x of the following sum, which is very similar to Riemannian sum. And this integral has good properties, namely, we know that its expectation is equal to 0. And we know that expectation of the square is equal to expectation of the moreover, we even can have a Newton-Leibniz formula in this framework, but of course it must be slightly corrected. And looks like the following. If we consider f from w t, for example, or excuse me, f from this integral from 0 to t xs dws t, then we deduce that it is equal to f from 0, 0 plus integral from 0 to t f prime 1. I will not write arguments, they are the same, only up to the very s multiply xs ws plus plus the next integral from 0 to t f prime 2 here is dt ds plus this is a new term which arises due to Wiener process here, 1/2 integral from 0 to t which respects the first derivative, and here is x squared ds. So this is an Ito formula. And based on this formula, previous properties of Ito stochastic integral, one can consider build very rich and very wide theory of stochastic differential equation. Namely, one can consider the equation like this: dxt is equal to a xt dt or no, plus b xt dwt, and there exists a rich theory of such equations. So you can ask why we need something else. We already know how to work with a very wide family of the Gaussian of the linear functionals, and we know that such stochastic differential equations are appropriate for physical applications, and we know that the solution can describe different diffusion processes. Moreover, the name of the solution as Markov process here is diffusion due to its relation with physics. So we can think that all our previous efforts and abstract construction are not necessary, but it is not true. Let me show you at least two questions, two simple questions, which to solve which we need or at least can use very effectively the technique which we've used before. There are several questions. For example, the first one. When x has density, xt has density, and if this question is more or less simple in one-dimensional case, in a multi-dimensional case, when this is a vector, this is a matrix, and this is a vector process, it becomes to be not very clear. And as we mentioned on our first lecture, it is related to Hermander hypoelectricity condition, and it is not too easy to solve it. And it occurs that using stochastic calculus, which we built, This question can be answered more or less easily and with a unified approach. Well, the next one also reflects some physical problems. As we have seen, main feature of the random function which we consider is that it is adapted to the flow of the signal fields generated by the Wiener process W. It is from one side, it is reasonable because one can consider these increments of W as a random perturbation acting on our dynamic system during its evolution. So it is natural that the resulting coordinate or position of our point depend only on the past of these increments. But one can imagine some other problems from physics. For example, suppose that we have a random string with two fixed ends. Then, when we will try to find the equation for this random string, which is moving under the random perturbation, the condition that we are adapted to the increments of W from the past now looks like not necessary and even non-physical. So let me ask you, what happens if initial condition x0 is a functional from the W1 phase? So we face a lot of new problems. First of all, we already lose the property that xt is adapted to the past of W. So we have to define new kind of integral, and then we have to discuss the existence and the properties of the solution. So you can see that despite of the well-developed and very rich and very efficient theory of stochastic differential equation in Ito sense, we have some questions which still needs some additional tools, and as these tools, we can use our Gaussian stochastic analysis. So let us begin. And today we begin with the understanding what is the meaning of the elements of our construction in the partial case related to Wiener process. So I will suppose that as initial Hilbert space H, we will have the space of real valued square integrate functions. I prefer 0, 1, but of course it can be arbitrary interval or even half of the line from 0 to infinity. Inner product is defined as usual, this integral from the product of the functions. And now it's time to define the Gaussian white noise related to the standard Wiener process W small. How will we define? Now let us proceed as follows. You remember that we have two descriptions of our generalized Gaussian random element in infinite dimensional Hilbert space or Gaussian white noise. The one is based on the family of independent standard normal variables and some orthonormal basis. Another one is the following. We just have a family H psi, and this family has some good properties. So let me recall. It is linear with respect to the first coordinate, and the result is a Gaussian random variable with the parameters 0 and variance equal norm of H squared. So I suppose to have this one using Wiener process. How I will do this? Let me proceed as follows. Consider firstly element of our L2. Very simple. It will be a step function. So h of t now is equal to sum from k equals 0 to n minus 1 ak indicator of tk plus 1 from k. Here is repetition 0 equal 0 less than tn equal to 1. I am not paying attention to these brackets because we have elements from H2 and it does not matter how it looks like at some fixed point. So we have such a function ht. Now let us define h psi. This is the definition as a sum from k equals 0 to n minus 1 ak w tk plus 1 minus w. By the way, this is a natural definition of the integral in this case, and it can be written as an integral from our function h t dwt. I just recall that we have to be careful with the definition of the integral because, as you know from the course of the random processes, that w has infinite variation. So when we will discuss some integrals with respect to w, these are not the integrals Riemann Stieltjes or X Stieltjes. But still, this sum, of course, is properly defined. Moreover, one can check that H side has a required distribution. So it has normal distribution with 0 mean and norm of H square as a variance. Due to this property, one can proceed as follows. Now, let us take arbitrary h from our space. And then consider the sequence of step functions such that it approximates h n tends to infinity. Then, due to this property, we have a limit of h and psi, and one can define h psi as a two limit h and psi. Of course, it must be checked that this limit not only exists but doesn't depend on the choice of the approximating sequence, but it can be easily done, and please do this as an exercise. So we have such a H psi with the same properties, and we get the desired family. Now one can say that we have a desired family, H psi. I still will denote it by integral from 0 to 1 H S dws. H belongs to 0, 1. Since we have such a definition, and as you remember, the inner product in L201 can be at least formally written as follows: HS psi S ds. Of course, I remember that psi does not exist. This is just formal recalling. But let's compare this formula and this formula. And if we consider, if we see these two terms, then it is natural to say that psi of S is just W dot S. Like formal derivative of linear process with respect to time. It doesn't exist, you know this. But in this sense, it can be defined at least as something which acts on the elements of L2. More, further we will see that this formal derivative of W can be considered as a proper random element in Schwarz space of distributions. But we don't need it. We don't need it right now. So I just show you this formal expression and formal notation because you can find it in literature. Since we have the family of Gaussian random variables related to white noise, so we define it, we can begin our construction. So let us try to understand what is the chaotic expansion for our random variables. To do this, we will proceed as usual, as before. Let me recall you that we began to discuss chaotic representation, examples of chaotic representation, with the simplest but very important family of random variables. Namely, we began with the discussion of chaotic expansion with the family of stochastic exponents. Let us do the same in this case. Yeah? So let us understand what is the stochastic exponent in this case. As we know, the definition of stochastic exponent looks like this is exponent with h psi minus 1/2 of the norm of h squared. Now I will suppose that we have psi generated by our linear process W, then we can continue this general formula to in our partial case, and we will get the integral from 0 to 1 hs dws minus 1/2 of the integral from 0 to 1 h squared s. Okay, let's yeah, squared ds. Okay. So when we see such an expression and having in mind definition of this integral, one can think about application of theta formula to this expression. Yes, we recall it today, the Ito formula for Ito stochastic integral. And let me emphasize that this is also Ito stochastic integral because H now is deterministic. And of course, it is adapted to any flow, sigma flows. So one can say that here we have Ito stochastic integral. Yeah? From this point of view, one can try to apply Ito formula to this expression in order to get the feeling what is it. And let me do this in a very simple partial case. First of all, this partial case will be full. I will suppose that H is totally equal to 1. And I will write this formula when here I have integral from 0 to t. Namely, I will consider the following random process wt minus 1/2 of t. This is simplest stochastic exponent. And now let us apply Ito formula to this expression. What we will get? We will get the following relation. It will be equal to 1. This is value at the point 0 plus. First of all, we have to put here integral from 0 to t. Then derivative with respect to w of this expression. It is the same. E ws minus 1/2 of s dw. Then I put here minus because what we need the derivative with respect to the second coordinate t minus 1/2 of the integral from 0 to t e w t minus ws ws minus 1/2 of s ds plus, you remember that in the case of Ito formula, due to the properties of Wiener process W, we must have additional term comparing the usual Newton-Raphel plus 1/2. And here we must put the integral with respect from 0 to t. Here we must have second derivative of this function with respect to w, and this second derivative is equal to the same function. So we have again ws minus 1/2 of s and ds. And you see that these two terms are cancelled. Finally, one can get the following relationship. That our stochastic exponent is equal 0t EWS minus 1/2 S dWS. It means that we have an equation, usual differential, stochastic differential equation for our stochastic exponent. We recall it stochastic differential equation in the beginning of the lecture today. Moreover, for us, it will be useful now to consider stochastic exponent with some parameter. So exactly in the same way, I can get the following. If I take any lambda which belongs to R and consider the process xt indexed by lambda equal the stochastic exponent of the following kind: lambda t minus lambda square divided by 2t, then one can say that dx lambda t is equal lambda x lambda t dwt, and the initial condition x lambda 0 is equal to 1. Okay. Okay, so you see that we have such Cauchy problem for our stochastic exponent with the parameter lambda. By the way, this equation explains again the name stochastic exponent, because this equation is very similar to the usual equation for the exponent. If we consider here dt, then we get as a solution e lambda t, so usual exponent. So from this point of view, it is reasonable to name this process of this one by stochastic exponent. This is one of the sources of this name. Since we have the stochastic differential equation for this exponent, one can try to solve it. And maybe it is not necessary to be an expert in the theory of stochastic differential equation in order to understand that this equation can be easily solved by the iteration method. Yeah, it is linear, so there are no any problem to get the solution as a limit of the successful iterations. Let's do it. So I will consider x lambda 0 t is totally equal to 1, initial condition, and then I will define xn plus 1 lambda t as 1 plus lambda integral from 0 to t x lambda ns dws. I just insist that everywhere here we have Ito integral. Then let us see the precise form of this successful iteration, how it looks like. X, let us try to view first. X1 lambda t will be equal 1 plus lambda integral from 0 to t dw. I prefer as 1. Yeah. Then x lambda 2t will be equal 1 plus what I must have lambda. Here is integral from 0 to t. And here I must substitute this expression. So I will write 1 plus lambda integral from 0 to S2, dWS1, and then dWS2. Finally, I will get the following. I will get the following. 1 plus lambda integral from 0 to t dw. I must write here S2, but the index does not matter, so I will keep here notation S1 plus double integral lambda square. Here is double integral from 0 to t 0 to S1, and here is d S2. Excuse me, S2. Here is S2, dWS1, dWS2. So what we have for the second iteration, it is expressed as sum the integral of the first order, this iterated integral, and from this maybe everybody can easily at least imagine, but it is desired proof that final expression is for x lambda t is a sum from kn equals 0 to infinity, and here is lambda n, and here is integral. I will write it like this one, this simple, this notation. I will explain what is it. dWS1, dWSN. Here I use notation delta n t is a simplex, so this is a set of points S1, Sn, such that 0 is less than S1, and so on, Sn less or equals to t. It's simplex. And I insist that here we have a good integral. Yeah, we just take this integral subsequently, and every time we have the integral for the past of the Wiener process. So it is in the framework of Ito construction, and these integrals are well defined. Moreover, this series converge in square mean, and moreover, one can check that these summas are orthogonal, by the way. So let us recall now that x lambda t is a stochastic exponent. I will write it as follows with the vertical sign of equality. Here is e lambda wt minus lambda square divided by 2t. Yeah. Okay. So let me recall now that this function looks like a generating function for Hermite polynomials. In order to get the real generating function for Hermite polynomials, we have to make a trick which we already did. I will divide here on the square root of t and multiply. So what we have the following. We have the following. E lambda square root of t, here wt divided on square root of t, and minus 1/2 lambda square root of t in square. Now we are ready to apply the fact that this is a purely Hermite polynomial generated function, and continue to write our formula and get the following series. It's equal to the sum n equals 0 to infinity. Here is lambda n power t and n over 2 n factorial hn wt over square root of t. That's all. Okay. But now let us compare to these series, because they are series of the same function, of the same random variable. Since lambda is arbitrary, we must have the equality of the coefficients. Yeah? So I can write that now we have the following relationship, that t n over 2 divided by n factorial hn of w t square root of t is equal to integral delta nt dw s1 dw sn. So what we can see that firstly, the integral with respect to simplex of the Wiener iterated integral with the Wiener process is nothing else than Hermite polynomial. Yeah. Second, this is chaotic expansion which we mentioned, yeah, because we already viewed it, and we know that this is exactly chaotic expansion of our stochastic exponent. Since then, we understand that at least in this partial case, our chaotic expansion consists of multiple Wiener integrals. Why I am saying Wiener integral? Because Ito presented general construction, as we mentioned before, when the integrated function is a random function adapted to the flow of the Wiener process. But Wiener already, maybe it was like 1923, considered integrals of such kind, only such kind. You see, this is a special kind of Ito construction. So Wiener already defines this integral before Ito. And we see that elements of chaotic expansion are the Wiener integrals. And it occurs to be true in general case too. And we will see in the next lecture that elements of chaotic expansion of our random variables, which are measured with respect to white noise, or another word, with respect to Wiener processes, are the multiple integrals, multiple Wiener integrals. So we have such a nice formula, which can be a starting point for the next lecture. For today, this is all. Thank you for attention. Maybe somebody have questions, please.